Welcome back. We are at the Energy Evolution Exchange. This mic? We're at the Energy Evolution Exchange stage here at OTC 26. And our next guest, I am very excited to introduce to you. It is Peter Richards. Peter is the CEO of Deep Manufacturing. And he is here to speak about large format WAAM for low volume, high integrity structures in demanding offshore and subsea environments. Please welcome to the stage, Peter Richards.
Thank you. So, is the mic on? Yeah. If I just get that going, and then that again. If I go back. So, just to address first question is the term WAAM. So it's wire arc additive manufacturing, because there's been a number of questions already, even before I started, in terms of what does the terminology stand for. So what I'll take you through briefly over the next 15 to 20 minutes is really an oversight of how we're using wire arc additive manufacturing in our own products and services, and now how we're applying that into the industry as well, particularly into the subsea sector. So basically, our existence is all around building low volume, large scale component parts. So ultra large scale parts through additive manufacturing. Now initially, our build requirements were for our parent company, and we were building pressure vessels for our parent company, Deep, to enable them to advance subsea exploration. And we've now built the capability through that internal customer to actually be able to sell our services into the external market, which is what we're doing now. So in terms of what we've been producing ourselves is we've now just finalised our first pressure vessel for human occupation. This is the first wire arc additive manufactured pressure vessel that is certified to the DNV standard and is pressure tested to 200 metres. So a world's first in terms of using the technology to be able to deploy it at scale. And what you can see here is the added advantage that the technology has is speed. So it's speed and design flexibility, because we're able to produce a component part that is roughly 6,000 pounds in mass in 45 days. And if you compared that to a cast or a forged part, you would be looking at substantially extended lead times to be able to produce a component at that scale. So that's been our first component part, which is actually on show in our factory in Houston. Currently at the moment, and it's using a variety of different materials as well. So we've used a carbon steel, so P355, Inconel 625, and also duplex within the build process. So the beauty of the build process is you can mix and match materials within that existing build. In terms of what we can physically do, the cells that we have and the way that we're able to produce component parts, we can really produce parts that are roughly in terms of volume, 9 feet by 9 feet, and also a part mass of around about 20 tonnes on our single cells that we operate. What you see behind me here is a cylinder being built, and also a nickel aluminium bronze propeller blade that we're also producing at the moment. The other point that we then have with our build process is the ability to enclose our actual cells, so that we can then cope with more exotic materials such as titanium, which are giving off other gases. So we've got that completely in a controlled environment within our facilities. In terms of being able to support complex geometries, we also then use manipulator tables, because basically what we're doing here is we're keeping the robot arm still and we're moving the part. So as you can see on the first side of the chart, we're basically building a cylinder here that goes up to 10 tonnes in weight. And then on the right-hand side of the chart, you've got one of the hemispheres, so the end of a hull that we're producing. Those hemispheres are taking us roughly around about 14 to 15 days to produce. So quite transformational from a speed point of view in terms of being able to get a product out to market compared to, again, a cast part from that perspective. The other point that we've perfected is then the use of multi-robot arms in a synchronized manner. So basically what we can do here is we've taken 6 arms, we've now coordinated the prints of those arms, and as you can see here, we are now producing parts that have a diameter up to 20 feet in diameter. So this is unique to Deep Manufacturing in terms of the scale that we can produce, and also the weight of the parts that we can produce as well. So we can go up to a maximum part mass here of roughly 30 tons in weight from a production point of view. The other ability that we've got is then to do more advanced welding technology. So what you see on here is one of our first pieces of infrastructure, which is the roller bot, which basically enables us to do internal circumferential welds within an existing hull structure. And we automate that process. We're now adapting that technology to actually be able to build and print on the horizontal. So the gantry system that you see at the bottom of the chart, that will basically be commissioned next month, where we'll have that availability to do, in essence, full hybrid manufacturing. And as you can see on the bottom right-hand part of the chart, it's the recovery module that we've built is actually welded on the roller bot. And you can see that in situ on the bottom of the chart in front of you there. The way that we use the systems and the way that we operate is it is a standard welding arm that we're basically using with additive manufacturing. So the beauty of the system, though, has two elements within the actual build process. So one, we've got an infrared camera which is doing temperature scanning on each layer. And then secondly, we're also then scanning each layer within the build process. So what that means is, as the technology we're building layer by layer, you can measure and control the interpass temperature to get a better quality on the overall performance of the part itself, and certainly against a cast or a forged part, because if you have an imperfection within the build, you can basically stop the build process, grind back, and then continue. So you can identify if you've got an error within that build process. In terms of our facility here in Houston, we've made an investment of just under $10 million, total investment so far. Our facility actually launches tomorrow here in Houston. So we have an open house where customers will be on site tomorrow, where they'll actually be able to see the technology in action. You can see part of the infrastructure being installed behind me. But basically, in that facility, we have 4 single robotic arms. We have 2 manipulator tables. And also, in terms of lifting capability, we've got 2 cranes within the facility, which are giving us 35-ton and 25-ton lifting capability as well. The facility is now also fully 9001 compliant, and we're now ITAR registered as well, because that now gives us access into the defence marketplace, which is one of the key other industries that we're now starting to address with the technology. The other really important part of what we're doing is quality and certification. And we've worked extremely closely with our classifications body, DNV, to basically ensure that we have 3 tiers of classification in the way that we operate. Firstly, we go through basically an approval of manufacture. So our facility is approved by DNV for our standard manufacturing processes and the way that we work. We then take our wire feedstock, that is then certified by DNV as well, so we then get type approval on the feedstock. And then the component parts that we produce are then also certified by DNV. So we have 3 tiers of certification, ensuring that we have a really robust quality standard that applies to any component part that we produce. And also, that certification is mirrored across our facilities, both here in the US and also in the UK as well. What it means for us now is our approval of manufacture with DNV gives us basically certification for pressure hulls and PVHOs, high-strength steels for hull structures and equipment, and also boiler and pressure vessel steels as well. And we're also working towards the API standards as well to support our operations here. That's underpinned by basically the materials that we can support within our build process. So we run through at the moment aluminium, low alloy carbon steels, copper, stainless, and then also into nickel-based super alloys. And on our roadmap is also 718 and higher grade low alloy steels as well as titanium. So the flexibility that you have within the build process, because you're basically taking a wire feedstock, is exceptional compared to both traditional additive manufacturing, but also wider grade castings and forgings as well. The way that we operate is really broken down into our service capabilities, as you can see on the chart here, which ranges from repair of in-service components, reverse engineering where we can actually take a Faro arm, we can scan an existing product to then be able to generate a CAD to be able to actually rebuild the component part itself. Turnkey PVHO solutions, so from design all the way through to the actual build of the part. And then two interesting areas for us at the moment, hybrid manufacturing, so where we basically take the dumb steel and we will weld on top of that steel to give a greater component and flexibility from a design point of view, and then also into production parts. And that also then leads into design optimization, because what this process then gives you is far more flexibility within a build process to be able to have more complex geometries from a build point of view. In terms of our operating model, the way that we operate is really simple. From a client point of view, it's basically give us the CAD. We take the CAD drawing, we then produce the component parts. There is no CapEx investment required from our clients where we've made that investment in the technology and the infrastructure. So it offers a leaner and more resilient supply chain. Also, because of the earlier point around certification, we take the burden on certification from the client base point of view. And in essence, it provides a complete turnkey solution from design, fabrication, machining, and also testing. So looking at some of the component parts and commercial projects that we've got running at the moment, I'll go into a little bit more detail on our nickel aluminium bronze propeller blade that we're producing at the moment. But the print time on that part was roughly 13 days. And again, in the industrial sector, we're also looking at taking, as you can see on the component behind me here, which is basically hybrid manufactured. We're taking basically an existing cylinder and we're doing some of the more complex welds onto that cylinder. And then into the subsea sector, a BOP and also a turret, alongside more complex geometries and pipe work as well that we can produce. But the key transformational element here is the time that it actually takes to produce the component part. The speed that we can produce a certified component is exceptional because you're looking at days rather than weeks, rather than months from a positioning point of view. The nickel aluminium bronze propeller blade that you can see behind me here, basically this blade is a mass of roughly around about 910 pounds, and that blade was printed in 13 days. And what you can see on the chart behind me is in its WAAM state, so in the state that we deposit the actual material, and in the machine state as well. So you've got that, while you can see the golder part of the part is where it's been machined back, so we can actually illustrate how it will look in its machine component state. And that part is now sitting in our facility here in Houston as well. So really just driving towards the end of the presentation before going to questions. In essence, our offering is really split into 4 key areas. One, it's around scale, so our ability to produce ultra-large scale parts at speed, underpinned by quality, but with design versatility baked into the way that we operate. And where we operate is then broken down into 2 core geographic areas at the moment, which is we have a centre of excellence based out of Bristol in the UK, and our facility here in Houston. And then we then have on our roadmap to be expanding into the Middle East and also into the Asia-Pacific region. So, thank you for your attention. I'll now hand back to Amy, and I think we'll move into a couple of questions.
Thanks, Peter. You can come join me right over here. Well, my first question was going to be, where's your accent? But I'm guessing Bristol, maybe, since you put that on the map.
UK, yeah, not UK, Bristol. Yeah.
Not Bristol.
Bristol's got a very peculiar accent, but we won't go into that. But yeah.
That's what always happens when you ask someone who's from the UK. So obviously, we want to talk specifically about the oil and gas audience, because that's why we're here. So where do you see the clearest fit for Deep's technology in this field and with this audience?
Yeah, I think it's basically addressing the point of transforming supply chains, because as I illustrated earlier, the speed that we can produce a component part, where there's a bottleneck in supply chain from that point of view, it's quite transformational from that perspective. So there's an opportunity there to really open up your delivery from that perspective. Secondly, again, it goes back into design versatility, because what we can also do within the build process is combine complex materials within that single build. So the part that I think is still on the or was on the chart earlier is we're using Inconel cladding within the build process. So we're going from mild steel into Inconel within the same build, and we're not having to change things from that point of view. So that gives real flexibility from a speed point of view and design flexibility. And then the third area is then really in terms of, if you look at within the oil and gas sector, the amount of spare parts that are kept in warehouses for resilience, purely on the grounds that if there's a failure, they need to deploy that part quickly. The beauty that this technology has is you can get to delivery of a part in, literally weeks, maybe into months, compared to what we're looking at with current component parts. We're seeing some customers that are on a 40-month lead time for a component part, be that cast or forged. This transforms it, because you're then talking, you can deliver that part within weeks or even months in its near net shape and the new machine back in terms of what's required.
And normally the forging or casting is a much longer process.
Correct. And also from a casting point of view, there's no guarantee that when the part comes out of the cast, it's true to the original requirements. It could have failures within it. The beauty of our process is, because you're going additive, we're reviewing each layer as it's built. So if there is any porosity in the build, we'll address that. So you're moving towards a higher grade of certainty on the quality of the part.
Okay. Can you talk a little bit more about some of the components that are best suited for the DED ARC WAAM manufacturing, and which components are less suited?
Yeah, ultimately, I'll address your last question first.
Okay.
It's large-scale parts.
Okay.
So ultimately, we can produce parts which are roughly, and forgive me, I don't know in feet, but in meters, so roughly about a meter in size is really where you've got a sweet spot for the technology from that point of view. Secondly, when you come back to component parts, it's really looking at parts that are critical within the overall operation and have a supply chain risk to them as well. Because the biggest thing here is speed in terms of the ability to deliver that part quickly. And then the third area is then design flexibility, because we can manipulate the part, so we're able to produce more complex geometries within a single build process than you could do with, say, even an intricate cast or mold for a cast. So that also gives flexibility in terms of from an opportunity point of view as well.
Customer service is so important. So can you talk a little bit more about how DEEP addresses qualification, testing, and then customer assurance as well?
Yep. So basically, from our point of view, we work really closely with DNV. We've gone slower to go faster in terms of our relationship with them in regards to ensuring that all of our processes are qualified. Also, our material feedstock is type certified as well, and also into the component parts. So DNV are on site in both of our facilities, in both the UK and here in the States, roughly every 2 weeks in terms of witnessing the build process that we go through. So they will stamp the start of an overall build, and they will be working with us through that complete journey. So from a confidence level then, from a customer point of view, they know they've got an independent third party that has then validated the overall build process.
Assuming that there's someone here in the audience today, or perhaps watching on our live stream around the world, if they're first hearing about DEEP manufacturing for the first time, never heard of it before, what would you tell them is the best first project or an engagement to start with?
Yeah, I think you need to be looking at, have you got a critical component part that you have a supply chain issue with? And if you've got a CAD drawing, log on to deepmanufacturing.com and send us the CAD. And we'll be able to assess whether or not we can produce that part and respond quickly on that basis.
All right, Peter Richards, anything else you want to add?
No, I'm good. Thank you. Thanks, Amy.
Fantastic. Thank you. CEO of DEEP Manufacturing, congratulations on the new building.
Thank you.
Tomorrow, I hope lots of people can go take a tour.
Super. That's great. Thanks, Amy.
Thanks for your time.
Appreciate it. Cheers. Thank you.